In the previous couple of videos, we discussed performing the unshift operation, which basically used for adding the node in front of the single linked list, right? That means that in front of the existing head node of the single linked list, we are trying to add a new value or new node with the help of a unshift operation. Now in this video, let's try to understand a function which basically removes the node in front of the single linked list. That operation is nothing but the shift operation. So as part of the shift operation, what exactly we will do is we will basically try to delete the very first node that we have on the singly linked list. That means that we will try to delete the node that is available at head of the singly linked list. Okay, so that is the purpose of the shift operation. Here we will not be taking any arguments from the user. In the end, we will simply return the node that we have removed. That means that whatever the previous head node that we had, right, that we will return as a output. Okay, that is the functionality definition. Now let's just see what all are the different cases that can occur when we try to implement the shift operation. Obviously, the first scenario that could come is basically the singly linked list is empty. That means that there are no nodes at all on the singly linked list on which we are trying to perform the shift operation. And we know how can we check if the singly linked list is empty or not, right? We have made a separate video for that. If you haven't checked it out, you can check that out. But anyway, we know how we can basically check if the singly linked list is empty. If it is empty, obviously, if the singly linked list is empty, how can we actually delete the very first node, right? And head and tail will be at null or none based on our programming language that we are using for implementation, and length will be at 0. So obviously in this case we will not be able to perform shift operation or the removing the first node in the singly linked list. So we will simply return null or none. Okay, so that is the first scenario. And the second scenario is basically where we have only one node inside the singly linked list. If we have only one node in the singly linked list, right, we will have both head and tail node at the same node. That's why we have to make sure that whatever the only node that we are having, that itself we are deleting. That means that singly linked list is becoming empty. So to represent an empty singly linked list, what we will do, we will assign head and tail both with null or none. That's why here if we have only one node, update head and tail both with null or none. So null is basically for the people who are using Java or JavaScript, and none is for the people whoever is using Python for implementation. Okay, so that is something that we have to remember. Along with assigning, what we have to do, we have to make sure that length also we are updating it with 0, because whatever the only node that we have, we are deleting that. As a result, single linked list becoming empty, which is nothing but 0. The length has become 0. Here, before assigning null, you can actually read the head node, because in the end we have to return the node that we are deleting, right? So just for returning that node, before assigning head and tail and length with the appropriate values, make sure that you are reading the head value, so that in the end you can return that value, return the value of head, or you can return the node itself. Okay, that is based on your choice. Okay, this is the first scenario where we have only one node, and the third scenario is obviously greater than one node inside the singly linked list. In that case, what exactly we will do is we are trying to delete the very first node inside the singly linked list, right? So we basically have the impact on the head reference that we are maintaining inside the singly linked list, because whatever the node that is at the head, that itself we have to delete. To delete that, what we will do is whatever the next node that is there after the current head node, that node we will update it to the head of the singly linked list. In this way, we are basically losing the track of the previous head that we are having on a singly linked list. So simple operation, simple assignment operation. Here we have to delete the node that is at the head. That's why we will make sure that whatever the next node that is there from the current head, we will simply update that to head of the singly linked list. Because we are maintaining head and tail of the singly linked list, our head will be pointing to the node that is at the second position basically. In that way, from head to tail we still have the singly linked list, and whatever the node that was there previously as a head, that will get deleted. Okay, so that is the algorithm for removing the or performing the shift operation when we have more than one node. What we will do, we will simply update the head to the next of the head node dot next. Okay, that is something that you can simply do using a simple assignment operation. Along with that, we have to make sure that since we are deleting one node from the singly linked list, we have to make sure that we are decrementing the length by 1. So length will be length minus 1. Okay, so that is those are the scenarios that could come when we try to remove the very first node of a singly linked list. Okay, now let's just try to write the pseudocode for shift operation. Okay, so as part of the shift operation, our aim is to delete the very first node that we have on the singly linked list. Obviously here, what we will do, we will write a function called shift, and this function will not take any argument because it knows that it has to delete the very first node in the singly linked list. That's why we will not take any argument. So as part of the first check, what we have to do, we have to check if the singly linked list is empty. If at all, if the singly linked list is empty, we will simply return null or none based on the programming language that we are using for implementing. Okay, that is the first scenario. And the second scenario is basically we have only one node. That means we know the length of the singly linked list, right? Whatever the length that we are maintaining, if it is equal to 1, that means that singly linked list has only one node in it. Otherwise, the other comparison that you can do is basically if you have only one node, we will make sure that both head and tail are pointing to the same node, right? So the other comparison that you can do is head is equal to tail also you can do, because both will be at the same point, at the same node. As a result, they will match. But I tend to use the length based comparison for checking if the singly linked list has only one value or not. If at all, if we have only one value, what we will do, whatever the head node that we have, we will update it to null/none, and similarly we will also update tail node to null or none. Here one thing that you have to remember is none is for the people who are using Python for implementation, and null is for the people who are using Java or JavaScript for implementation. Okay, so that is something that you just have to remember. Anywhere I am using null or none, it is for the specific people, whoever is using the respective programming language like I mentioned previously. Okay, after updating head and tail, we will update length to 0, because whatever the only node that was there on the singly linked list, we have deleted that. As a result, the singly linked list has become empty. As a result, the length will be 0. So this is the case where we have only one node in the singly linked list. Now let's just try to handle the otherwise case where we have more than one node in the singly linked list. In that case, like I mentioned previously, what we will do, we will simply update the head with the whatever the next node we have from the existing head of the singly linked list. This is the head node and this is the tail node. Let's assume that we have 3 nodes on a singly linked list and we have to delete the very first node. So we will, if we want to delete, we will simply move the head to the next node. In that way, we will lose this, the head that we had previously. That's why we will simply update head with the head node dot next. Okay, and we have to make sure that we are decrementing the length also by 1. Okay, so that is something that you have to remember here. And couple of people, what exactly they will do is, here we already had the next node on the previous head, right? To make that also null, first what exactly they will do is they will read the current head is nothing but the head, right? Now on this, after updating the head node, what exactly they will do is they will also set current head dot next to null or none. Okay, so this is some optional operation, you don't have to do it, but just some people are very particular about updating the next to null or none based on our the way we are implementing. They will make sure they try to update the next of the whatever the head node that we had previously, because in the end we have to return the node that we are deleting, right? That is nothing but the current head. If we simply return the complete head, the complete node, using the next, user still has a possibility to traverse the remaining singly linked list. So they just don't want to give that functionality. As a result, before returning that value, they will make sure that they assign next to with null or none. In the end, we will simply return whatever the current head that we have inside the current head variable, which will basically have whatever the value we had at the head node in the singly linked list. Okay, so that is the implementation of a shift functionality on a singly linked list, which is basically used for removing the very first node we have on a singly linked list. Okay, now that we have written the pseudocode, let's go ahead and let's try to write the programmatic implementation of that. So inside the singly linked list implementation that we have written earlier, there I will be adding a new function called shift. Okay, and this function will not take any argument because it will obviously delete the very first node in the singly linked list if we have any nodes in the linked list. So if you remember the pseudocode that we have discussed earlier clearly, right, there could be three scenarios when you're trying to delete the very first node in the singly linked list. Those three scenarios are basically you either are trying to delete the node or the very first node in a linked list where there are no values at all, that is the singly linked list is empty. And the second scenario is you are trying to perform the shift operation on a linked list where we have only one node. And the third scenario is trying to perform the shift operation on a linked list where you have more than one node in the singly linked list. If we can write the implementation which can honor these three cases, right, so your implementation will be done. Now let's go one by one case and let's try to implement the same. So as part of the first case, we basically need to check if the singly linked list is empty, right? If so, obviously we can't delete anything in an empty singly linked list because there are no nodes at all. So how will we check? Basically in that case, either head or tail will be pointing to null or the length will be equal to 0. So in the previous implementations we have already done head based comparison, right? In this video let me do length based comparison so that we would have used all the possible comparison that could be possible for a empty singly linked list. If this is the case, obviously since there are no values, we will simply return null, indicating that there are no nodes at all. If this is not the case, then we could check for the situation where we are trying to perform the shift operation on a linked list where we have only one value. How will we know if we have only one value in the singly linked list? Both head and tail will be pointing to the same node that is in the singly linked list, or the length of the linked list will be 1. So in this video, I'll go ahead with the length based comparison. If the linked list length is 1, okay, basically that only node itself we are deleting. That means head and tail will become null. Since as part of the shift operation, we need to return the node that we are deleting, right? For that, let me just read that into some variable current head equal to this dot head. It will actually get us the head node. Now once we have that, we need to delete the only node that is existing. That means head and tail will become null, indicating that list is empty in the further operations. So head equal to null and this dot tail equal to null, and since there are no values, obviously the length will become this dot length equal to 0. Okay, in the end we need to return the node that we have deleted, which is current head. Okay, so we have completed the second scenario also. If none of these two scenarios match, that means in the else condition, that means we are trying to perform the shift operation on a linked list where we have more than one node in the single linked list. In that case, what we need to do, we have current head. The next node of the current head should be the new head of the singly linked list, and we have to make sure that we are assigning the next of current head next variable to null, so that it will get deleted. So for that, what I will do is, first I will simply take const current head. I'm reading the head node of the singly linked list, okay, and the next head will be, that is next head. It will be the next of the current head, that is the next node of the current head, which can be accessed from the current head dot next. Okay, this new head will be the new head of the singly linked list. So for that, what I will do, simply I'll take this dot head will be the next head of the singly linked list, and we have to assign the next of this current head to null. Current head dot next equal to null. Okay, at the end of the day, we are deleting one node from the single linked list. That means the length will decrease by 1. So this dot length equal to this dot length minus 1. Okay, in the end we need to return the node that we have deleted, that is nothing but current head node. Okay, so we have written the logic for supporting 3 possible cases that we have discussed. Okay, this is how basically we perform the shift operation on a singly linked list. Now let me go ahead and execute it and validate the results. For that, let me just go on to this terminal. Let me just clear out all this, and let me just uncomment all these push functionalities so that we will have some values in the linked list. And let me just comment out this unshift operation that we have called earlier. So on the singly linked list object, let me just call the shift operation. If you observe the shift operation, the values on the singly linked list, the head node is 10 and we have totally 4 values, and the tail node is 10.134. So if we perform this shift operation, since we have more than one value, right, obviously this 10 will get deleted, and the new head of the singly linked list will be codingpal.arg, and the tail will be whatever we have earlier, which is 10.134. If we execute this, we should see the same thing. Node singly linked lists and singly linked list.js. Okay, if you observe here, after shift we have traversed the singly linked list. As a result, it got printed. In that result list, the head node is codingpal.arg and the tail is 10.134, and the total number of nodes are 3, or the size is 3. Okay, this is a shift operation on a linked list where we have more than one value in the linked list. Now let me just comment out these 3 push functions. So we have only one value in the single linked list. If we try to delete the only one value, the list will become empty, right? So the head and tail will be null. If we try to read the dot value, we will basically get the null pointer related exceptions. So I'm just removing dot values. So if we just print SLL dot head and tail, it should basically give us null, and the length will be 0 because linked list is empty. So if I execute this, we perform shift operation. So we deleted the only existing node, and the traverse operation basically goes to each and every node and prints the values in that single linked list, right? Since there are no nodes, we've printed nothing. After that, we've printed this separator, and as part of this print statement, we have basically printed null, null and 0. Okay, if you want to capture the node that we are deleting also, you can simply receive it const removed node. Okay, and you can log it if you want, console.log removed node. Okay, if I execute it, you should see the node that we have deleted, which is 10. Okay, do you see we have printed the node that we have deleted? If you do remove dot value, you will basically get the only value, which is 10. Okay, so even if we try to perform the shift operation on a linked list where there are no nodes, that means we will remove this. Let me just, because we are trying to print the null that is going to return. So simply if I execute, I'll get null because there are no nodes at all, so we are simply returning null. So as part of removed log print, we've got the null, and traverse did not print anything. We've got the line separator, and we've got null, null and 0 as part of the last print statement. Okay, this is how we basically perform the shift operation on a singly linked list, or we basically try to remove the very first node in the singly linked list. Okay, I hope you are able to understand. So just like in every video I mentioned, go on and try to perform the combination of operations that we have implemented so far. Call them and see if we are maintaining the consistency across the singly linked list, and after performing each and every operation you are able to see the valid result set in the singly linked list by calling the traverse function. Okay, I will leave it to you guys, and you can do it on your free time. Okay, now that we have implemented the shift operation on a singly linked list, let's just try to analyze the time complexity and space complexity of the same. So you might be wondering, what is the best case and what is the worst case of implementing the shift operation, right? When we try to perform the shift operation on a singly linked list, there will not be any best case or worst case, because we are trying to delete the very first node on the singly linked list itself. Because even if the singly linked list has n number of nodes, even if the singly linked list has only one node, the operation is very similar. When we had only one node, we will simply update the head and tail and length with appropriate values. Even if we have more than one node, or even if we have n nodes, we will simply update the head node to the next of the current head that we are having. So obviously, be it the singly linked list where we have only one node, or be it the singly linked list where we have n number of nodes, we will simply delete the very first node by using the simple update operations. As a result, the time complexity will be order of 1 only. Okay, so now let's talk about the space complexity involved in performing the shift operation. So if you remember, we have basically defined a variable called current head, right, where we tried reading the head node. Besides this read operation, and we after this read operation, we have basically updated the head node with the head node dot next that we already had inside the singly linked list. The only memory that we are consuming is for this variable where we are trying to read the head node, so that in the end that node is getting deleted, right? Basically we have to return in the end. So obviously that variable will take only constant amount of memory. And even if you take the scenario where we have only one node also, we are updating the head, tail and length that we are maintaining. We are updating it with the appropriate values with null or none and 0. So those update operations will take only constant amount of memory for implementation, right? So even if the singly linked list has only one node, even if the singly linked list has n number of nodes, whatever the shift operation that we are trying to perform will take only constant amount of space for implementation. Okay, that's all there is in terms of time and space complexity analysis of a shift operation on a singly linked list. Okay, so thanks for watching. I'll see you in the next functionality implementation.